Today we're discussing Module 1, Cluster 1, Proficiency 1A, classifying numbers. So to classify numbers within the real number system, we need to understand what the real number system is. And this is represented by this diagram here, where you can see we have this outer circle, which constitutes all the real numbers. So anything in this blue section is a real number. Then we have two sections within the real numbers. We have irrational numbers over here, kind of in this tannish color, and that is numbers that are square roots that can't simplify, decimals that don't repeat and do not truncate. So if I have a decimal that is 3.759 and it keeps going on forever without repeating, that would be an irrational number. Pi is an irrational number because it never repeats and it never ends, it never truncates. That's the word we use in math. So all those are irrational numbers. Then we have rational numbers. So anything within this circle, and you can see that integers, whole numbers, and natural numbers are all within this rational number circle. They're still rational numbers. So rational is anything that can be represented as a fraction. So 7/3, we have 7/3 here. -5/9 is rational. And then as we move down into these inner circles, you might think, well, -7 is not a fraction, but if we wrote it as -14/2, isn't that a fraction? It is a fraction, but it reduces to -7, and so all integers, all whole numbers, and all natural numbers are also rational numbers. So what exactly are integers? Well, integers are all the negative numbers, 0, and all the positive numbers. So the positive numbers we call natural numbers. The first numbers we learned are counting numbers, 1, 2, 3, 4, 5, 6, 7, 8, 9, all the way forever. And then whole numbers are just all the natural numbers with 0. Integers are all the inverses of the natural numbers. So those three sets can all be written as fractions. They're all considered rational. And all the numbers we've talked about in this slide are all real numbers. We'll get to imaginary numbers later on in this course. So let's do some examples. We're going to classify these sets of numbers. So let's start with example 1. We have -√1. A square root means two numbers that multiply together to give us this interior number. So can we think of two numbers that multiply to 1? Well, yeah, if we factor this, this is the same thing as 1 times 1. So the square root here is just 1, so this is -1. We can rewrite it as -1. Then we have these other numbers that are represented as fractions. So if we're working with these fractions, what we want to see is we want to know, are they going to reduce down and become natural numbers or whole numbers or integers, or are they going to stay as fractions? Because that'll adjust the way that we classify these. So I've got 112 divided by 32. If I convert that to a mixed number, that's really 3.5. So that's going to stay a rational number. It doesn't become an integer. It does not become a whole number. It does not become a natural number. It's still just rational. When I do 24/3, that reduces to 8. So this is a whole number and an integer and a natural number. And I have -2, which is an integer. So what I want to do when I classify is I want to figure out what class do all these numbers fit into. Well, are they all natural numbers? 1, 2, 3, 4, 5, 6, 7 on forever? No, they're not. Are they all whole numbers, which is 0, 1, 2, 3, 4, 5, 6, 7 on forever? No, they're not. Are they integers, which is all the positive whole numbers, 0, and then all those numbers negated, all those numbers as negatives? Well, that would be true, except we have 3.5. So that does not fit into integers, whole numbers, and natural numbers. So that means that what we're really left with is a set of rational numbers, and all rational numbers are real. And these have abbreviations. So if you see like a letter Q, that's the abbreviation for a rational number. And the letter R is the abbreviation for a real number. So we've classified these as real rational numbers. Let's go to example 2. In example 2, we have a whole bunch of square roots. So we're going to do the same thing again with these square roots. We're going to see if these square roots can simplify. So this is the square root of 80. If it was the square root of 81, it would be a perfect square and it would simplify to 9. This doesn't. So immediately, because it's a square root that doesn't simplify, I know that these are going to be, this at least, is going to be an irrational number. So this is irrational, which is abbreviated as I. 57 is not a perfect square. We know that because 64 is a perfect square, and so is 49, and 57 is in between them. So that's the square root of 49 is 7, the square root of 64 is 8. If it's in between them, it cannot be an integer. So this is also irrational. Here we have a fraction inside, 20 divided by 2, which is 10. Square root of 10 is also irrational because we know that the square root of 9 is 3 and the square root of 16 is 4. And in between 3 and 4, there are no integers. And then we have over here e. And we use this number to create things like natural logs. It's a naturally occurring number, and it's a decimal. It's a representation of a decimal that does not repeat and does not end. It does not truncate. So that's also irrational. So we have found all these are irrational, and they're also all real. So irrational and real. Let's do example 3. All these are nice numbers we're used to working with. Some are negatives, some are positives, but they're all kind of nice numbers. So thinking of our classifications, these are definitely not irrational. So these are definitely rational numbers. We know that these are going to be rational. Each one of these I can represent as a fraction. 15, maybe I represent 15 as 45. Negative 45 over 3 would be negative 15. 7 is maybe 14 over 2. Negative 3 is maybe negative 9 over 3. And then 101 is maybe 202 divided by 2. And so these can all be written as fractions, so they're rational. Are they integers? Well, they are integers because integers include 1, 2, 3, 4, 5, 6, 7 on forever, plus 0, plus all the negative numbers in there. Well, 3, negative, that's an integer. 15, but negative, that's an integer. 7's an integer, 101's an integer. So these are definitely integers. Are they all whole numbers? Well, because we have these negatives here, negative 15 and negative 3, they are not whole numbers. They do not fit in that whole number category because they have these negatives, which makes them exclusively integers. So we know that these are rational numbers, they're integers, and they're also real. All the numbers we're talking about are real numbers right now. So the abbreviation for rational is Q. The abbreviation for integers is Z. That's a Z, not a 2. I'll put a little dash through the middle. And then we have real numbers, which is represented by R. So that's what we have here for example 3. Example 4. This is an integer. When I divide 60 divided by 5, it comes out really nicely to 12, because they're both negatives. So this is also an integer. This is a truncated decimal, a terminated decimal. So we know that this is actually going to be rational. So we'll just go ahead and say integer, integer, rational. And the square root of 4 is 2, which is also an integer. And a whole number, and a natural number. So looking at what all these share, all of these, because they are fall into integers, we know that they're also rational. But because we have this truncating decimal here, it's not a whole number, it's not an integer, it's not a natural number. So this falls into the set of real rationals. Here we go again. We have pi. This is going to be irrational. E we've already talked about. irrational. Square root of 5 is not a perfect square, irrational. And then here we have a decimal that does not repeat 18171915, and this dot 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 means it hasn't truncated after 5. It continues on. We can't write numbers forever, so we stop at that point. So this is also irrational. So we have a set of irrational numbers that are also real. Example 6. The square root of 36 is 6. 18 divided by 9 is 2. We have 7. And then 4.44 divided by 4.44 is 1. Any number divided by itself is 1. These are all positive. They're all greater than 0, which places these in the category of natural numbers. Well, if they're natural numbers, they're also whole numbers. If they're whole numbers, they're also integers. That's a Z. If they're integers, they're also rationals, and they are also real. So this example 6, covers several sets. Example 7. In example 7, it's similar to example 6, except it's more straightforward. 7, 11, 31, and 15 are all natural numbers. And because they're natural, we know that they're also whole. Because they're whole, we know that they are also integers. This should be a Z. They're also integers. Let me try that one more time. A Z. Because they're integers, we know they are also rational, and rationals are also real. Example 8. In example 8, we have several square roots, which makes us think if none of these can be simplified, this is going to be an irrational set. But as we begin to look at it and simplify, the square root of 0 is 0. The square root of 169 is 13. The square root of 16 is 4. And the square root of 121 is 11. We have 0 and onward, so these are whole numbers. They're not natural numbers because we have 0, but we have whole numbers, which are also integers, which are also rational, which are also real. Example 9. 28 divided by 2 is negative 14. Then we have 9. Then we have 76 divided by 8. 76 divided by 8 is 9.5 or 9.5. So this stays kind of as a fraction, but we'll just call it 9.5. And then we have 208 divided by 224, which can be simplified and reduced, but it's going to remain as a fraction. We know that because the numerator is smaller than the denominator. So this stays as a fraction. So because we have fractions in here, we know that these are rational, and we know that they're also real. Example 10. This is our last example. We go ahead and look at these. Square root of 81 is 9, so this is negative 9. Then we have negative 10, 5/6, which cannot reduce, and then 240 over 2, which reduces to 120. But because 121 is a perfect square root, we know that 120 is not a perfect square root and cannot be simplified. So this set is probably the most tricky because in this set we have an irrational number. This is irrational, can't be simplified. And then we have these rational numbers. So we can't classify them as irrational numbers or rational numbers because they have both, and they're mutually exclusive. They're separate sets that don't overlap. So these are just simply real numbers.